Hello everyone, my name is Bhupendra Kumar Aherwal and today we are going to discuss about the discrete log problem and its application in cryptography. So in today's presentation we will start from the introduction part and history. We will discuss about what is DLP and what are the algorithm to solve the DLP, and mainly we will focus on the Pohlig-Hellman algorithm, their examples, then assignment problem, and later we will see the application of DLP, then useful links, and finally the references. Let's start with the introduction part. The discrete log problem, the subject of interest among many mathematicians and cryptographers in the recent times because it is computationally infeasible to find. And any cryptographic algorithm that provide the security, it is based on the assumption that there are some mathematical problems that are difficult to find or difficult to solve. That's why we have used it. So let's see something about the history of the cryptography. So the cryptography is not a new concept. We are using to listen it from the 200 to 300 BC, since from the Roman and Egypt Empire. But the origin of the modern cryptography comes from the 20th century, where Reverse Samuel Diffie-Hellman proposed their ideas in field of public key cryptography that is secure enough. So before we move to our topic, first we see some aspects of the security. When two entities or two parties wants to communicate with each other or they want to send data, so first thing they need is the data privacy during the communication. Nobody wants that their data should be known to the third one. The second thing is authenticity. So during the communication, you should know that you are communicating with a dedicated person or the desired one, not the fraudulent one. So in this picture, you can see that Neo wants to communicate with Trinity, but there is some intruder, new client Smith, who can take the identity of Trinity and communicate like the Trinity with Neo. In public key cryptography, we have two pair of keys for each user. One is public key and one is private key. Public key is known to everyone, so the user can encrypt the message using either the public key or a private key. So if a user encrypt the message using its private key, then it is possible to decrypt the message using the receiver's public key that is known to everyone. So it will not be secure enough. So what he can do, he can encrypt the public key of the receiver and the receiver will decrypt the message using its private key. So this will provide the security. So let's discuss about our main course. What is discrete log problem? So there are two problems on which public key cryptography is used. That is, first one, it is very difficult to factorize the value of n in RSA crypto system, and it is very difficult to find the discrete log value in Diffie-Hellman key exchange and algorithm crypto system. So what is discrete log? So let's consider a finite cyclic group for any element alpha and beta belongs to G having order n, and if A is a generator, then A power alpha power I, where I belongs to 1 to n minus 1. So discrete log problem is to find the unique integer I such that alpha power I equal to the beta. So the value I equal to log beta to the base of alpha. So the I is called as a discrete log. So in terms of modulo concatenation, we can written it as alpha power I equal to beta mod n. So the question comes in our mind that why we are using discrete log in public key cryptography. So there are some aspects that makes the computational difficult. First is it is computationally hard to find the value of I, and if we choose a group properly, like generic group in which the elements are the multiplication of the prime numbers. And third one is a one-way property, that is it is difficult to find the value of y if we have x, but it's very difficult to find the value of x if we have y. Let's take an example to understand what is discrete log. Suppose we have a multiplicator group of order p, where the p value is 56529, and let's 2 is the generator of the group. So how we are going to calculate the discrete log value with respect to the value of h? So it is computationally difficult to find by hand, but for using a computer, it is difficult. It is easy to solve. That log h to the base p equal to the 11,235. So you can verify it by taking the power of 2 power 11,235 mod 56,509 equal to 38,679. So it will give the same value as h. So there are certain algorithms given to solve the discrete log value. The function field sieve, index calculus, number field sieve, Pollard algorithm, Pollard-Kangaroo algorithm, quantum algorithm by Peter. So today we are going to discuss about the Pohlig-Hellman algorithm. So for all these algorithms, the complexity is very high. So please remember that any cryptography algorithm is not very easy to generate an attack in polynomial time. There will be always a exponential time, and the number of attempts is depends on the key size. So let's start with what is Pohlig-Hellman algorithm. For this algorithm, we have input in a form of modular conjugate relation, and we have to find the value of x that will satisfy the conjugate relation. So before to understand the algorithm, you should revise about the what is Euclidean format theorem and what is Chinese remainder theorem. So please take a brief recap of these algorithms, and let's come to our algorithm. First, we have to factorize the value of p. The phi of p is a Euler-Twisted function, and its value will be p minus 1. And we have to factorize in the multiplication of prime numbers. Uh, we have given the congruent solution, and we are taking value x equal to the a0 plus p1 a1, and let's assume that we are factorizing with only two prime numbers, that's p1 and p2. So using the given converse relation, we are putting the value of x, and we are powering the whole relation with the p2. So we will get this expression, and use after using the uh, Fermat's little theorem, we will find the expression like a power p2 whole power a0 equal to b power p2 mod p. So since we can easily find the value of a power p2 and b power p2, only thing we have to determine the value of a0 by hit and trial method. And since we have x equal to a0 plus a1 p1, so after calculating the value of a0, we will find a congruent relation like like that, x congruent to a0 mod p1. So similarly, we can take the x equal to b0 plus p2 p1, and we'll find a similar another congruent relation as x congruent to b0 mod p2. And using the Chinese remainder theorem, you can solve these uh, congruent solutions and you can find the value of x. So this is the flow diagram of the Pohlig-Hellman algorithm in broad way. We are factorizing the value of phi of p in k prime numbers. So there will be k or congruent solutions, and using the Chinese remainder theorem, you can find the value of x. So let's take a simple problem for understanding the algorithm. We have a problem that the power x is modulo congruent to 22 mod 31. So first we have to factorize the value of phi of p. So we are factorizing the 30 into 5 into 6, that is two prime numbers, and GCD of 5 and 6 should be 1. And after that we will take the value of x in terms of a0 plus 5a1, and putting the value of this into the given equation and powering the whole equation with respect to the 6. So we will get the equation that like uh, like that 3 power 6 whole power a0 into 3 power 30 into a1 equal to 20 power 6 31 or 31. So after simplifying it and by applying the Fermat's-Little theorem, we will get the 3 power 6 whole power a0 equal to the 22 power 6 mod 31. And simply we can calculate 3 power 6 mod 31 will be the 16, and 22 to the power 6 mod 31 will be the 8. So we will find the expression that 16 to the power a0 is equal to the 8 mod 31. So here we have to find the value of a0. So we are applying the trial and error method, finding the value of a0. So by trial and error we will find the value of a0 equal to the 2. So 16 to the power 2 equal to modulo congruent to 8 mod 31. So we will find the uh, expression such that x is modulo congruent to 5 mod 2. So we will take it as a equation number 1. Similarly, take the value of x equal to the b0 plus 6b1, and we will put the value of x into the given equation. So after solving this, we will find the expression 26 power b0 is modulo congruent to 6 mod m 31. So we have to find the value of b0 by we are applying the trial and error method. So here we are getting the value of b0 equal to the 5. So b0 will be the 5, and we will find another congruent solution. X is modulo congruent to 5 mod 6. So we have two congruent solution to solve. So we are applying the Chinese remainder theorem. So after applying the Chinese remainder theorem, we will get the smallest integer x equal to the 17. That will satisfy the both equations, and we are putting the value of 17 into the given problem. So the one solution will be the x equal to the 17. So it is not the only solution. We have infinite number of values of x. So in cryptography, it is very difficult to find the value of a unique value of x. So this is the not the only way we can solve this problem. We can divide the 30 into 2 into 3 into 5. There will be more number of solutions, and there also we will apply the Chinese remainder theorem and find the value of x. In public key cryptography, the value of p will not be the small. We are supposed to take a very large value of p, let's say is 1024 bits, and it is very difficult to factorize it and find the unique value of x to generate an attack. Let's take a problem as assignment for your practice. The problem is 71 power x is congruent to 210 modulo 251. So you need to find the value of x. So for the solution of this, you can refer to the book, The Handbook of Applied Cryptography by Alfred J. Manis, the fifth edition. Also, you can find the detail about the Chinese remainder theorem and Euclidean-Fermat's little theorem. Let's see some areas where the discrete problem is applicable. First one is the algorithmic crypto system. Second is Diffie-Hellman key exchange. Third one is digital signature. So these are the useful links. You can refer to the MIT open course. The second one is the video lectures on cryptography and network security by Dr. D. Mukhopadhyay. And you can refer to the book of handbook of applied cryptography. And there is some Wikipedia links and YouTube links also. And these are the references I have referred. I hope it is helpful for you. Please like, comment, and give your feedback on my YouTube channel. And thanks for watching. Thank you.